So let's finish up what we were talking about last time. And there's always a lot of confusion on the term molecular shape because it gets confused with electron geometry, molecular shape. And so, and different sources use different words. So we're just going to all agree that when I say molecular shape, I want what the molecule looks like if you took it with a magic camera that could see the molecule, but it wouldn't be able to see where the lone pairs are. So the electrons are still going to use VSEPR to get as far away from each other as possible, but we can't see them when we take that picture. So that's what I mean by shape. By the way, if you're not enrolled in the class, pass your exam down to somebody else because, and you can still work the problem, but we don't need to get your grade because you're not enrolled in the class. All right? I want to make sure that happens. Okay. So for example, molecular shape. So with ammonia, we've got 4 groups. Those 4 groups want to get as far away from each other as possible, so they're going to establish a tetrahedral geometry. That's the farthest apart that they can get. So the groups, yes, so the electron geometry, if you want to call it that, or the groups are at the corners of a tetrahedron. But when we want the molecular shape of ammonia, it's trigonal pyramid. Because again, that camera we're talking about is going to take a picture that's going to look like that for ammonia. Everybody see that? So that's what I want for molecular shape. So let's look at water. So water here, well, we start off with the Lewis structure.
Might run out.
Might run out. So there are 358 people in the class, and I made 370 exams. So if you are not enrolled, you still can do it with everybody else, but please pass your exam to somebody. It's not an exam. Please pass your problem to somebody that's enrolled in the class. If you are enrolled in the class and somebody's already penciled in their name and ID and all of that kind of stuff, take out a piece of paper, put your name and ID, and I will hand enter it. Okay? That's all we can do. All right, and so next time we do something like this, make sure that you just pass the exam along if you're not enrolled in the class. All right, so water. We start off with the Lewis structure. And when you draw your Lewis structure, again, Lewis structures require that you draw all non-bonding electrons, all lone pairs. So make sure you do that, because if you don't put in the lone pairs, you're going to get the wrong prediction for the geometry of the molecule or the molecular shape. So as we can see, oxygen has 1, 2, 3, 4 groups. So we have 2 atoms and 2 sets of non-bonding electrons. So there's 4 groups around oxygen. Those groups want to get as far away from each other as possible, so the groups are at the corners of a tetrahedron. And so this is what it's going to look like. There's a couple different ways that we can draw, but there's one set of lone pairs, there's another set of lone pairs. This hydrogen, here's our oxygen-hydrogen bond. Here's our oxygen-hydrogen bond here. And so if we look at the molecular shape, we only have 2 atoms that oxygen is bonded to. So that would be like us going like this. No, right there. It's hard to see, it's so bright. Okay? So what would we call that molecular shape? Bent or angular. I've seen some books call it angular. So molecular shape. Bent or angular, I would accept both of those answers. All right, so if we drew out, now this technically is, it doesn't look like it, but this would be a 3D dash wedge. We don't have any dashes and wedges, we don't need to. 3D dash wedge. And the reason that's a 3D dash wedge is just because I'm actually attempting to show the correct bond angles when I draw it. If I was drawing a Lewis structure, I could have a right angle there. And so that would not be attempting to show the orientation. So I would call this a 3D dash wedge. What about the bond angle here? So it was 109.5 when we have the 4 groups here. When we have lone pairs, we actually condensed that bond angle a little, 107. Now we have 2 lone pairs. It's 105. So on the exam, I would want you to write approximately 105, approximately 107, or for this top one, 109.5. Rather than just saying 109.5 for everything, it's more correct to say, to try to get as close as you can as possible. So again, bond angles are smaller. Smaller still, because now there are 2 sets of lone pairs. All right, I want to summarize important points. Molecular shape or geometry. I will call it molecular shape on the test because geometry gets everybody confused. What's she talking about? Electron geometry? You know, what are we talking about here? So I'm going to use the word molecular shape. Describes the orientation of atoms in a molecule. Lone pairs are not included when naming geometry. Okay, so again, we're taking it with that magic camera. It takes a picture and the camera can't see lone pairs. They're still oriented in the same way. We're not ignoring lone pairs to predict where the groups are. We just can't see it with the camera. Lone pairs, non-bonding electrons take up more space than electrons in a bond. This condenses the bond angle from the ideal of 109.5. Questions? Anybody? All right, so now we're going to start our little in-class problem. I'm going to write it up here for those of you who don't have an exam, and next time we're not going to, you're not going to grab one if you're not enrolled in the class. So let me go ahead and write that up here. So nothing's stopping you from looking at your notes because this isn't a test, but I would try on your own to do it without looking at your notes, and that will give you an idea of how up to date you are with where you should be at this point in the class. So, all right, that's time. Put your pencils down, pass your exams to the nearest aisle. I think this kind of stuff is the most difficult part of midterm 1, I really do. So I wanted you just to kind of get an idea of what kind of questions I ask on the exam. I don't want you to come in on the exam day and be in a panic like, oh my God, I've never seen that before. You know, I'm freaked out. I don't want that to happen. So let's go through the answer. So it says, fill in the missing lone pairs on the following compound and then draw 2 resonance structures, including all formal charges and non-bonding electrons. Label major, minor, and very minor resonance structures. Then draw the hybrid. All right. So we know that nitrogen, and here's where these rules come in. Lone pairs are not required when we draw other types of ways to draw something. In a Lewis structure, we need the lone pairs and the charges. We know that nitrogen makes 3 bonds and has a pair of non-bonding electrons when it's neutral, so there has to be a lone pair here. We know that carbon, when it's negatively charged, makes 3 bonds, and it has a pair of non-bonding electrons. So there's a pair of non-bonding electrons. I'm going to draw this both ways. Who wants to see me draw all the hydrogens in? Okay, so you can do skeletal, but I'm going to draw all the hydrogens in. So I'll redo this down here. A good number of you need to see your hydrogens. So I'm just going to write CH3 here. I don't have to draw everything out. But I do know that for a negatively charged carbon, I will have a hydrogen here. I will have a lone pair, and there's my negative charge. And then I will have a CH3 here. So I'm just going to draw it that way. All right, so one of the things that we can do, and arrow pushing really helps when you're trying to go between resonance structures, And I notice I have this lone pair here, and I have a double bond that's sort of one bond away. And that's a situation where you can move electrons around. So I'm going to go here, and I'm going to move electrons up onto nitrogen here. That means now on that nitrogen I have 2 lone pairs. I now have a double bond between the carbon and between those 2 carbons. There's my hydrogen, CH3 here. Okay, so that's one resonance structure. Do we have any charges here? We should. All resonance structures should have the same charge. So we have a negative charge on this overall on this resonance structure. That means we need a negative charge overall on this resonance structure. So nitrogen, for the purposes of calculating formal charge, nitrogen owns 1 electron from every covalent bond, and it owns all of its lone pairs. So nitrogen owns 1, 2, 3, 4, 5, 6. Nitrogen is group 5, so it has an extra electron. That's where our negative charge is. All right. The other thing we can do, and I'm going to draw the arrows on this first resonance structure. I'll just use a different color. The other thing we can do is we can break this pi bond. And when we break a pi bond like that, we can move electrons. We want to move electrons onto the more electronegative atom. So we have a bond between nitrogen and carbon here. Nitrogen's more electronegative. So I would just go like this and move electrons that way. That's going to give me a third resonance structure. So there's that negatively charged nitrogen again, which we can compare with the one that's on the left-hand side to the left of that. And we're still going to have this negatively charged carbon. And now we're going to have a positively charged carbon with no octet. So we want to label major, minor, very minor, and certainly I hope that everybody can see that that third resonance structure is very minor. We have 1 less covalent bond. We have no octet on carbon, so this one's going to be very minor. Now between the 2 of these, what do you think? They both have the same number of bonds. All atoms have an octet, so then we go down to the third thing, which is looking at where the charge is. In the first resonance structure, we have a negative charge on carbon. In the second resonance structure, we have a negative charge on nitrogen. Nitrogen's more electronegative, so it's going to be happier with the negative charge. So this one is major, and this one is minor. All right, questions? So now all we have left is the hybrid. All right, so we want to draw first all of the bonds that aren't changing. So notice I'm doing half skeletal, half condensed, and that's okay as long as everything is conveyed. So we have a hydrogen here that's also not changing. So what we have here, if we look, this carbon-nitrogen double bond, carbon-nitrogen single, single, so that's going to be a partial bond. And then we have here carbon-carbon single, double, single, so that's going to be partial. And that's it, right, for the bonds. And now we need to do charges. So I'm going to look at each atom that's changing. We have nitrogen here, neutral, nitrogen negative, nitrogen negative. So that would be partial negative. And then we're going to look at carbon, neutral, neutral, positive charge for partial positive. And then carbon is negative, neutral, negative, so partial negative. Whoops. That's some of mine are permanent, some are not. Let's just change that too. That's partial negative there. Or let me just draw it all over again. How about that? That's better. Okay. Questions? Anybody? Now, notice I didn't worry about lone pairs on the hybrid structure. It makes it a lot easier to draw, and I'm not going to ask you to do that. Yes?
Do we have to draw the arrows on the midterm?
I want you to draw arrows on the midterm. I do. It helps you further on. Yeah. On the exam, you will be. On this one, here again, if you get about 3/4 of it or more, then you're going to get an extra point for it.
Also, do you want us to draw complete skeletal structures, or can you just?
You can do it however you want.
Okay.
Skeletal structures. At the beginning, they're hard, but it's going to be so second nature to you that you're going to have a hard time not drawing skeletal. So, and I did a combination of the two, which is really common for me. Yes?
How would you want us to arrow push to the third resonance structure if we don't have two colored pens to arrow?
Yeah, you know what? I'm going to make it a little easier. Yeah, that would be a hard one to grade for arrows.
Okay.
So yeah, I probably wouldn't grade arrows on something like that. Yeah. All right. Okay, let's move forward here. So that gives you an idea of the type of test questions that I ask. It also lets you know, wow, did I have to keep looking at my notes? I'm not really up to, I'm getting a little behind in the class, okay? All right. Next, we're going to talk about describing the orbitals used for bonding. Again, this is everything you ever wanted to know about organic molecules, looking at their structure. And the more we know about the structure, the more we're going to be able to predict reactivity, and that's our goal. So electrons, we need to not only describe the geometry, but we also need to know the orbitals used, because again, that's going to help us make predictions. So let's first describe the orbitals used in bonding. In order to understand structure, I already said that. Electrons have wave-like and particle-like properties, and this is where it gets a little strange and students start to shut down, because we don't have anything in our experience that's like this. So, but what it is it's a model that we have come up with to describe what molecules do. It's not a perfect model. It's based on observations that we've made about molecules, experiments that we've done. It's not a perfect model, and sometimes it breaks down, but it's the best model we have right now. So we're going to start with just talking about distribution of electrons in an atom, and then we're going to move to molecular orbitals, and then we're going to move to hybrid orbitals. So if you understand everything in this chapter that we're doing, you're going to be fine for what you need to know for organic chemistry. We are glossing over some things that you went into much more in depth in GChem. But again, this is the level that you need to know is the level that you will see in the notes. All right, so the exact position of an electron cannot be specified, only the probability that it occupies a certain region in space. So that's the Heisenberg uncertainty principle. And so this gets into quantum mechanics, and it describes the wave-like nature of electrons. A wave function is used to describe the motion of an electron in an atom or a molecule. And so this is a simple wave function. We're going to use psi to indicate the wave function. And right at this line here, this horizontal line, that's where the wave function is 0. If we go above that line, the phase is positive. And below that line, phase is negative. Now, this is something that you talk a lot about in physics. It's not, and some of you haven't had your college physics yet. So most of you, a lot of you take it next year. Don't worry about that. Just an understanding that waves have phases. All right. So in this wave function here, the wave function is positive in this region. Wave function is negative in this region. And when it crosses this horizontal axis, the wave function equals 0. And when we have that, we have a node. And a node is where we have 0 probability of finding an electron. So the positive and the minus do not imply charge. These are the phase of the wave function. And so when we draw these, when we draw orbitals, we'll very often draw them 2 different colors just to show that we have a different phase. The square of the wave function gives the probability of finding the electrons at a given distance and direction from the nucleus. And plots of psi squared in 3 dimensions generate the shapes of s, p, d, and f atomic orbitals, which we're going to look at in just a second. Electrons in an atom can be thought of as occupying a set of concentric shells that surround the nucleus. Each shell contains subshells, which are the atomic orbitals. All right. The energy of the atomic orbitals can be plotted. All right, so we have 1s orbitals. That's the first shell. Then we have 2s, higher in energy than a 1s, and the 2p is higher in energy than that. This is the second shell. And then over here we have the third shell. And then if we go over here, we have the fourth shell. And when we start getting up into the third and the fourth shell, it's things are pretty well behaved down here. We would expect the 1s to be more stable, closer to the nucleus. And then we have the 2s and the 2p. But now once we get into the third level, we have 3s, 3p. And the 4s is actually lower in energy than the 3d. And then once we get into the fourth level, we have the 4s here. We have the 4p. We have the 4d. And now the 5s is lower in energy. It gets a little confusing. Here's what we deal with in OCHEM. Right down here. Okay, so that's actually a lot easier. We're just dealing in this area. But you can see that once we get into the third shell, we can accommodate more than 8 electrons. So here's our octet rule. Here's our duet rule. The energy, in order to have more than 8 electrons, we'd have to start going into the third subshell, and it's too far away. So I want you to notice that as we go up higher shells here, higher energy levels, and the orbitals get a lot closer together. So it's easy for electrons to jump between orbitals. And so that's where you get that interesting behavior with transition metals. Do you remember that from GChem? Where the way they would fill up their orbitals is a little bit interesting. All right, so important points. First of all, I want you to notice energy levels get closer together as you get further from the nucleus. As you get farther from the nucleus, the energy levels get closer together. All right, also each orbital can hold 2 electrons. So the 1s orbital only can hold 2 electrons. That's the maximum we can exceed in the first shell. So first shell we have 1s orbital, and therefore it holds 2 electrons. Second shell, and again we're dealing with the first and the second shell pretty much almost exclusively in this class. We have 3 p's, so 4 orbitals altogether. Each can hold 2 electrons, and therefore we can hold a maximum of 8 electrons. And that's where we get our octet rule. Third shell, we have 1s orbital, 3s. We have 3p orbitals, so those are the 3p. We'd have the 3px, the 3py, the 3pz, and we have 5 ds. So that's 9 altogether. With 2 per orbital, we have 18 electrons. So if any of you are chemistry majors and you're going to go on and take inorganic chemistry, for this class, we have the octet rule For inorganic chemistry, you have the 18 electron rule. So very similar, okay? For shell, we have 1s, 3 p's, 5 d's, and 7 f's. So therefore, these hold 32 electrons. And again, most of OChem is in this range right here. By filling the orbitals with electrons, we arrive at the electron configuration of any atom in the periodic table. So let's do carbon. Okay, that's our favorite atom in this class. Mine anyway. So here's carbon. Atomic number 6. Since it's atomic number 6, then therefore it has 6 protons and 6 electrons. So now we can certainly have varying number of neutrons when we have isotopes of carbon. But if we have carbon, we had neutral carbon, 6 protons and 6 electrons. So what we're going to do is we're going to fill up the energy levels. Lowest energy is filled first. So there's 1, 2, maximum of 2 electrons per orbital with paired spins, Pauli exclusion principle. And degenerate orbitals are filled with 1 electron each before the electrons are paired. So these 2p orbitals are all the same energy. Because we have increasing energy here, they're all the same energy. So energy of the 3 2p orbitals is the same. Therefore, they are degenerate. So that means when we fill up the electrons in degenerate orbitals, we're going to put 1 electron in each orbital before we start pairing. All right, so we have 1, 2, 3, 4, 5, 6. So that would be the electron configuration for carbon. Questions on how I did that? Anybody? All right. Atomic orbitals. As we said previously, the square of the wave function gives the probability of finding an electron at a given distance and direction from the nucleus. So we can plot psi squared in 3 dimensions to generate the shapes of the s, p, and d, and f atomic orbitals. We're only going to look at the s and the p's because, again, that's all we really worry about. So you can see a couple of things. This is probably, hopefully, showing up better on your page. Yes, it is. All right, so now, I like these drawings because it shows a fuzzy border. And you're just going to see it with you just draw a line, and you see that line. It really is a fuzzy border. So this is what it would look like normally in most pictures. That doesn't, and so that's and when we draw that circle or show that circle even with a fuzzy border, that's where we have a 90% probability of finding an electron. 90% probability. Within the border. So that means that there is some possibility, although very small, of finding an electron outside of that border. So that's sort of our 90% mark. But I like the idea that it's fuzzy because it really is a fuzzy border. All right, so notice fuzzy border. All right, so we have, this is the 1s. This is the 2s. So the 2 just means we're now in the second subshell. And I'm just adding orbitals as we go. So here we have the 2s and the px. So we're adding them as we go. This would be them superimposed. This drawing is a little different because I usually, when I draw these, I have this be the Y and this be the X. And this be the Z, and this is just twisted a little bit, but it's the same idea. Okay, so here's our S, here's our PX, here's our PY, and here's our PZ. Here's our PY, and here's our PZ here. So that shows all of the electrons superimposed. All right, so that's the shape of the orbitals. Now, so that's atomic orbitals. Let's talk about molecular orbitals now. So when we make a covalent bond, it results from the combination of atomic orbitals to form molecular orbitals. So for atomic orbitals, we can abbreviate AO, and for molecular orbitals, we're going to abbreviate MO. A molecular orbital describes the volume in space around a molecule where an electron is likely to be found. So let's start real simple here. Let's look at the hydrogen. Making a hydrogen-hydrogen molecule. So molecular hydrogen. So we combine a hydrogen 1s and a hydrogen 1s, and we make a hydrogen-hydrogen bond. So here's what happens. We're going to start over here on the right and move to the left. So what happens is, here's our individual hydrogen 1s orbitals. And as they move together, so we're going to be moving together, starting from the right. These are going to move together and get closer together. And as those move together, notice the energy is dropping. So what's happening is, as these move together, the electron, so this hydrogen atom has one electron, right, in its valence shell. That electron in this valence shell starts to become attracted to the positively charged nucleus in the other atom. And that's an attractive force. So the closer they get together, the more that force that wants to pull those two together, the more the attractive force. A good analogy for this is if you have magnets, you take two magnets and you line them up so they're attracted, and you hold them out like this. And if they're strong magnets, you can't feel any attraction. But as you move closer and closer, probably don't feel it here, but right when you get about there, you can feel this force trying to pull those magnets together. And the closer you are, the stronger. And if they're really strong magnets, you might not be able to hold them this close. They might want to just, fly together, depending on how strong they are. So the closer the positive and the negative charge, obviously with magnets it's poles, the south pole, the north pole. The closer they are together, the stronger that attraction. So that's what's happening here. These are becoming attracted. They're moving closer here. They're moving closer. And as they're moving closer, that attractive thing makes the molecule more stable. And you reach a certain point where you have, this is the lowest energy possible, and that's where you have the maximum attractive force, but a minimum negative. All right, so what would be negative, and why do we jump really quickly here? If you brought those closer together, you're now going to have the two positively charged nucleuses are now really close to each other. They're going to repel, right? And so they're close enough that they can feel the other positively charged nucleus. That's a repulsion. So that's going to push it apart. So we've got this positive attraction, and we've got, when you get too close, repulsion. So this is the sweet spot here, where you have a maximum attraction and minimum repulsion. So let's write that down here. So as the hydrogen atoms move together, the electron from one atom is attracted to the positively charged nucleus of the other atom. And so the energy is dropping, energy is dropping, energy is dropping. Right here is the minimum energy. And that's a minimum energy because we have a maximum attraction and minimum repulsion. So maximum attraction and minimum repulsion of the two positively charged nuclei. If we look at this distance here, the dots are the nuclei. And if we look at that distance here, that distance is 0.74 angstroms for H2. And so we can add that over here. So when the two nuclei are 0.74 angstroms apart, that's the sweet spot, maximum attraction, minimum repulsion, and that is the bond length for hydrogen. Hydrogen-hydrogen bond. So this is the bond length. Bond length for a hydrogen-hydrogen bond. And so it turns out that if we have isolated atoms and we compare that with the energy of H2, it's 104 kcals per mole BDE for bond dissociation energy. So in order to break, the hydrogen-hydrogen bond, you need to provide 104 kcals per mole energy. (104 kcals per mole energy. So that's the bond dissociation energy for hydrogen-hydrogen molecules. So we really never see hydrogens uncombined. Naturally occurring hydrogen is going to be molecular hydrogen. All right, questions? Anybody? Yes?
Is that the same value for the bond enthalpy?
Excuse me?
Is 104 kcals per mole the same value for the bond enthalpy of hydrogen?
Yes. Yes. Okay. All right, now we're going to start talking about, well, what about the wave? The wave, they have particle-like, electrons have particle-like properties and wave-like properties, so let's not forget about the waves. Okay, so phase is important when you add together wave functions. So here are wave functions if you add two waves of the same phase. So we have phase 1 and phase 2. Those are the dotted ones. And when they add together and they're in the same phase, you get a bigger wave. So what we say is that the waves reinforce. So what that means is they add together to make a bigger wave. If, on the other hand, you add two waves of opposite phase, or out of phase, add two waves out of phase, some portions of the wave cancel each other out. So what we say is the waves interfere. Which means they partially cancel each other out, and a node is created. So here's the node right here that's created, and that's the place where you have a 0 probability of finding an electron. All right, that's time. We're going to stop right here, and we will continue this next time. I hope you have a great weekend.